Hello, I'm Sophie Rovner from the American Chemical Society. Welcome to this news briefing from the ACS Fall 2020 virtual meeting and expo. We're joined today by Dr. Guan from Beihang University. She is studying how mixing silk with polymers could lead to better biomedical implants. Dr. Guan.
Hello, everyone. I'm very glad to join this ACS press conference. Today, I'm going to talk about silk composites. So silk is an ancient material, but it's still young for man-made composites. So in our group, we make greener and tougher composites using these natural silks. Potentially, these silk composites could be used as a helmet, airplane structure panels, and car panels, even for civil engineering. Okay, next, Sophie. Okay, so in our group, we selected two very special silk fibers. One is from the common Bombyx mori silk fiber, and the other is from the wild silkworm silk called Anthera perni. So these two silk fibers are different. One is very white in color, and the other is very stretchy and very tough. So the wild silk is 5 times tougher than the common Bombyx cocoon. Okay, sorry, actually it's twice tougher. So the cocoon composites, natural cocoon composites, so the house for the silkworms is actually much tougher as well. So because humans cannot make these natural fibers without using silkworms, so we try to make use of these natural fibers to make composites to combine with epoxy resin polymers. And we got lots of polymers to choose, and epoxy resin can actually combine with silk very nicely to form very tough, strong composites. So we study silk because they have a very special characteristic structure. It contains both orderly crystal structure and also highly oriented amorphous structure. Okay, so these two silks are actually kind of a very tough material we can get from nature. So we hope to use these composites for more uses, and potentially if we can combine silk with more biopolymers, we can make better biomedical composites. Okay, Sophie, I have some specimens to show. Hi, so I've got here is a wild silk fiber samples. So we try to put these silk fibers into composites and combining with polymers. These are two composite samples. One is made of silk, wild silk, and the other is made of carbon fiber. So the silk composites is lighter in color and also lighter in weight. So we can also make lighter lattice structures like this. So this is made of silk fibers and epoxy resin polymers. So it's light, it's lighter than water. Okay, so it's very cool. So okay, that's all my introduction. Thank you, Sophie.
All right, thank you. At this point, I would like to invite questions from viewers. Please state your name and affiliation in the chat window when you type in your question. To get us started, I will begin with this question. How did you get the idea to mix silk with synthetic compounds, and have other researchers done this before?
Okay, so before I started to make silk composites, I actually studied for quite a long while the silk fibers. So I know they are special and unique. I know like people cannot make these fibers without using the animals. So I thought, okay, we have been using these silk fibers for textiles for thousands of years. And now we have developed composites for the last century. So why not we combine silk fibers with more versatile polymers to make a kind of a bio-friendly, biodegradable composites. So that was the beginning. And before us, people have done research on silk composites, but they used chopped kind of a particulate silk fibers. So short and chopped silk fibers or microfibers, not really continuous fibers. So the difference is with these continuous fibers in the composite, so they can more effectively transmit load and transfer load. So take up the load effectively. Thank you, Sophie.
And you've addressed this a little bit in what you just said, but if there's any more, please feel free to add about what's unique about your silk composite and why it's better than other silk composites being developed.
Okay, so our silk composite, in terms of mechanical performance, is superior. It's much better than the reported silk composites. So we can get a tensile strength of 300 megapascal. So this is a much higher than the reported tensile strength for other silk composites.
Which would be in roughly what range, do you think?
Okay, in okay, it's at least three times better, higher. Yeah. And the other point is we can, by using these continuous fibers, we can make more fiber content, higher fiber content in the composite. This would make silk composites kind of a more environmental friendly and greener. So yeah, it can be, because it's made of a protein, it can be degraded by the natural environment, and it is produced under very mild conditions by the animals.
Okay, and would these composites be safe to put into people?
Yes. We have, because for the moment, I've only studied the system of silk fibers combined with epoxy resin polymers. So to make epoxy resin polymers, we will start from small molecules. For these systems, if any residual small molecules remain in the system, it will be unsafe. But with biopolymers, for example, polylactic acids, they are kind of mimics of natural polymers. They can be absorbed, and they are perfectly safe for human body. And this new research is still undergoing.
Right. And so on the flip side of that, could you make permanent implants, or would you only be going after degradable implants?
I think we are aiming for degradable implants.
Can you talk a little bit about those?
We think one of the, compared to other natural fibers like fibers made from cotton, they can't be absorbed by the human body. So we think silk fibers made of proteins can be absorbed by the human body is kind of an advantage compared to other natural fibers of, for example, from plant source. So we try to reserve this feature. So we will aim to make a fully biodegradable. It's kind of a trend as well for the new medicine, biotherapy. I think they try to use different bioactives combining with a matrix like our silk composites to stimulate the function of the body to make new structures, new tissues. So it's better for the implanted structures to naturally degrade, I think.
And so what kind of applications do you picture there for implants that would degrade?
We are actually currently aiming for bone fixation devices. For example, you have a bone fracture from accident or other injuries, and your bone will actually amend itself in maximally 3 months. And within these 3 months, we hope the silk composites will degrade and be replaced by the natural tissue, natural bone tissue. Yeah, we are collaborating with the doctors to do this.
The press release mentioned spider silk. Have you tried that in your composites?
Okay, we actually tried. The problem with using spider silk is the quantity. It's too difficult to get large quantities of spider silks to make, useful composites. Even for our laboratory, we found it difficult to make kind of even a small cube of spider silk composites. They are really very fine. They are some fibers are less than 5 microns, and that's kind of only a very small fraction of your hair. So it's very thin, too difficult to get a large quantity. We have made some spider silk reinforced rubber films, but okay, that's just the application. We haven't found more ways to produce more spider silk, and it's really too pricey and expensive.
And how does that diameter compare to that of the other silk?
Okay, so silkworm silks are fatter, okay? So the common white silk is about 10 microns thick. So they don't have circular cross sections. They are kind of a triangular cross sections. That's why people often say the white silk has a kind of a luminescent color. It's kind of like a okay, I can't say that word. Yeah. So, but the other wild silk is much fatter too. So they probably is larger, thicker. They have a much larger diameter too.
All right. What are some challenges you need to overcome before these materials could be used?
For natural fibers, there's a variability issue actually. People often ask me how to get consistent fibers and how, I think we rely on the silk textile industry now. They produce very nice fibers and very consistent as well. And the other issue is the sensitivity to humidity. So we have done a study on that too. we found actually the silk can absorb water. That's even when you combine silk with polymers. But this kind of a effect on the property is kind of can be predicted. So even when you immerse the silk composite in water, it can still give you sufficient mechanical performance for kind of for certain structural applications.
And have you had any interaction with companies or explored any way to commercialize this technology?
Yes, actually, I've approached a biomedical device company, but the kind of the problem is really how to standardize the silk fibers. Okay, so at the moment we are still discussing. There are challenges for these fibers to be applied. Yes. Mm-hmm.
All right, well, thank you very much. The archived version of this session will soon be posted at www.acs.org/fall 2020 press conferences. Please join us for our next press conference at 10 a.m. today on cyborg technology that could enable new diagnostics and the merger of humans and AI. Thank you.